Hello and good day, Geometry. Here with you to go over math packet number 10, which is due on April 15th. Jumping right in here, a man entered an orchard that had 7 guards and picked some apples. When he left, he gave the first guard half his apples and 1 apple more. To the second guard, he gave half his remaining apples and 1 apple more. He did the same to each of the remaining 5 guards and left the orchard with 1 apple. How many apples did he gather in all, or how many apples did he start with? So if you started your algebra packet and watched the video, the first couple logic questions had to do with a working backwards technique. We're going to apply the same thing here because when you leave this orchard, okay, all the guards are done. We'll call guard 0. You've got 1 apple remaining. That's what you leave with. Which means how many apples did you have when you approached the first guard? Which actually we're going to kind of, we should label that with a 7 because it's actually the 7th guard that you come across here. Very heavily guarded apple orchard for whatever reason. So it says here that to each of the guards, and we'll work all the way back to the first one, 5, 4, 3, 2, and there's the first guard there. You give half your apples and 1 apple more. So how many apples would you have had to have so that at the 7th guard, you gave the guard half of your apples plus 1 more, and you left with 1? Well, your gut answer here might be 3 apples, okay? Because if you give 1 more, but you realize that doesn't work because then you're dealing with fractional values. So, or half. You can't give half an apple. So for starters here, you know that all of your answers working your way back to the original how many apples that you picked all have to be even because you can't give half and not an odd number of apples. Okay, so it turns out that you had 4 apples when you approached guard number 7 because giving the guard half of your apples, 2, plus 1 more, 3, you gave that guard 3 apples, and so you're left with 1. Well, how many apples did you have when you approached guard 6? That you gave the guard half of your apples, plus 1 more, and you were left with 4. Well, that answer is 10. You give the guard half of your apples, 5, plus 1 more, a total of 6 apples given, and you'd be left with 4. Okay. The next one. You approach guard 5. How many apples would you have to have so that you give the guard half of your apples plus 1 more, and you're left with 10? Well, here that answer is 22. Because you give the guard half your apples, that's 11, plus 1 more, that's 12 apples given, and you're left with 10. So I'm going to let you do the rest from here. Perhaps you are seeing some patterns develop here that you can kind of carry with you throughout. Maybe you can even identify the formula, the expression for this that represents how many apples you've got left at each given guard. That can be a little challenge for you. You don't have to do that, but if you want to go the extra mile, if you get bored over spring break, then you can go that route. But ultimately, the question is, how many apples do you have when you approach that first guard, right? So that you can start this give half plus 1 more, and you leave with just 1 apple. So generous of you. It's very, very kind. Next question. How many squares are contained in the image below? Oh, you gotta love these. How many squares are contained in the image below? You probably started by counting, you've got 1, 2, 3, 4, 5, 6, 7, 8 across, 1, 2, 3, 4, 5, 6, 7, 8 down the side. So that's 64 total. Oh, plus the big one, right? Can't forget about, that's always the one people miss, the big square. There's 65. 65 squares. Well, okay. But what about all the 2x2 squares? What about all the 3x3 squares? Or the 4x4s? Or the 5x5s? Or so on and so forth. Oh boy, now all of a sudden doesn't seem quite so simple. Okay, but here's what I advise you to do. Start with the number of 1x1 squares, right? Because that's easy to count. It's just 8 across, 8 down. there are a total of 64. Now I want you to look for the number of 2 by 2 squares. And I'll outline the first 2 by 2 square here in green. Remember, here's the second 2 by 2 square in blue. Here's another 2 by 2 square outlined in red. Okay, these squares can overlap here because it is a different 2 by 2 square. I'll outline another 2 by 2 square in red. Going down here, that's another 2 by 2 square. So I've already outlined 4 2 by 2 squares here. What you're going to find as you start to count these up, and really all the work is figuring out the number of 2 by 2 squares and maybe even the number of 3 by 3 squares. Once you do that, you should notice there's a certain pattern developing so that you don't necessarily have to count all the 4 by 4s or the 5 by 5s or the 6 by 6s or the 7 by 7s, or, as we already figured out, there is only one 8 by 8 square. That's the entire square. That's the whole figure, right? So you do have an endpoint here. We've got the 1 by 1s. We've got the 8 by 8s. Your job is to figure out the number of 2 by 2s, 3 by 3s. Again, look for that pattern to develop here. And the ultimate answer is the sum of all of these values that you find here, right? That's going to represent the total number of squares. Enjoy. On to our 5-card challenge. We've got an ace. Make a 2. Not much more to say about this question here. Percentage of the area that is shaded. This very topical, very good timing for this, as we just finished up our unit on special right triangles. And it's not labeled, which is what we would have told you in class here, but all of these triangles, that one there, this one here, all these white triangles going around the figure, they are all 45, 45, 90 triangles, okay? So they're acute angles, 45, 45, can't really fit them here, 45 here, 45 there, so on and so forth. All those angles are 45 degree angles. These are all right angles here as you go around, okay, kind of fill them in here. And if you remember the relationships that 45, 45, 90 triangles have, you can use the given values here, okay, to calculate the areas of each of those triangles, which you can ultimately use to get the area of the shaded section. So the area of the figure, the whole figure, is the square here, right? This is the figure. That's the area of the square, and the shaded region is that area minus all those white right triangles that'll leave you with the shaded section in the end. So there you go. 45, 45, 90 triangles are your key. Then we go on to the pattern block question. We already covered this in the algebra video, but your job is to complete the table. Do remember there's a very distinct pattern with this total block figure. This is our 4th packet, I believe now, dealing with squares. And so you can kind of look back at previous packets to help you there if you need it, but very distinct pattern there. And since only one color changes in each figure, and you know which color that is because it's consistent, there's a pattern there too, it's almost like an equation, right? Got 1 yellow, no pink, no blue, no red, 1 yellow, still 1 yellow in figure 2. We've added 8 pink, no blue, no red, there are 9 total. In figure 3, we know there are 25 total. We know there's 1 yellow. We know there's 8 pink. We haven't added any red yet. So this is almost like an equation to calculate how many blue there are, right? 1 plus 8 plus something plus 0 has to equal 25. And that's where we can fill in the missing value for blue blocks, which is 16. And you can kind of continue that thought process through the rest of the table. You are making a graph for this. It says create a graph showing the relationship between a figure and the number of yellow, pink, blue, red, and total blocks in the figure. So your graph should have 5 lines on it. 1 representing the red, red, but yellow, the pink, the blue, the red, and ultimately the total. Okay. Your figure number is the x-axis, and the number of blocks in each figure is the y-axis, with each of the 5 lines on it. You can share with me if you want to on the Google, call it pattern number 10, or you can print it out in color, please, and attach it to your packet. Next up, we have our shaded area question. And in algebra, the surface area was only of the 3 rectangles, but now I give you the surface area of the figure. So in the algebra packet, we talked about the 3 rectangles. Their areas are represented by 10 times x, right? The length times the width here for that side rectangle. The one on the other side is another 10 times x, because it's the same size. The rectangle on the bottom has a width of 12 and a length of x, or length of 12, width of x, however you want to say it. And so those three terms represent the areas of the rectangular faces. But now for the areas of the triangular faces, which is half times base times height, we actually have all the information that we need here, right? The area of this triangular face, which is 1/2 times the base 12 times the height 8, equals 48. And since the other triangle on the other end is the same size, that will have an area of 48 as well. So this is going to be your expression now, which is equal to 756. I don't believe, in fact, I'm very confident that your value for x for geometry is not the same value for x that you got for algebra. So you do need to solve this equation again, because x is going to be different. And then from there, calculate the volume of the triangular prism. Don't forget to draw a net of the figure. Whether you do that in algebra or geometry doesn't make a difference, as long as you let me know which one it's in. But please answer your algebra packet question in your algebra packet, and your geometry packet question here in your geometry packet. Don't put them both on the same packet page, because how I correct them, it doesn't work out well. So there you go. Then we get to the Magnificent 7, where you are calculating the different values of 5 of these 7 shapes. I talked about this a little bit more in the algebra packet, so see that if you've got questions, or come talk to me. But yeah, write the formula down for each of them, and then what values get you that formula, 5 of the 7. Now we come to our math exploration page, talking about different combinations, okay? And in your algebra packet, we talk about the Fibonacci sequence. Here, we're talking about Pascal's triangle, which is yet another pattern of great mathematical significance that's pretty easy to figure out. Pascal's triangle, kind of like Fibonacci, each number in the triangle is the sum of the 2 numbers above it. So like this 10 comes from the sum of 4 and 6. This 21 comes from the sum of 15 and 6. This 84 comes from 28 and 56. So that's kind of how Pascal's triangle is created. And here's what we're doing in this today. Starting at the top here. My kids get a snack on their way to daycare in the morning and are allowed to choose 2 of the following options: artichokes, burritos, or coconuts. And the question is, how many different combinations of snacks exist? So I've listed this out. I intentionally started these with different letters so we can make this as easy on ourselves as possible. But the different options are artichokes and burritos, artichokes and coconuts, or burritos and coconuts. That's it, right? Burritos and artichokes is the same combination as artichokes and burritos, so I don't write BA down there. I don't even have a C column here because coconuts and artichokes, CA, is the same as AC, and so on and so forth. So 3 total combinations for that. Okay, let's say you have 4 cats: Appleton, Bowser, Cat, and Dumbledore, A, B, C, D, and can bring 2 to the vet at a time. How many different combinations of cats exist? Well, you've got Appleton and Bowser, which is the same as Bowser-Appleton, which is why there's no BA combo in that B column there. You've got Appleton and Cat. You've got Appleton and Dumbledore. Those are all the combinations with bringing Appleton. You can pair Appleton with Bowser, with Cat, or with Dumbledore. If you start with Bowser, we already have the Bowser-Appleton combo, so we don't write that a second time, but we don't have Bowser and Cat, or Bowser and Dumbledore. When we start with Cat, we already have Cat and Appleton, right? The CA is the same as the AC here, so we don't write that down. We have CB. You can't bring CC because it's the same Cat. So the only combo for column C here is Cat and Dumbledore. We don't have a column D because every combination involving Dumbledore has already been written down in a previous column. So there are a total of 6 combinations here. And note how I organized my list. As with any time when I ask you to list a lot of things, if you tackle it in an organized manner, it makes it a lot easier to keep track of what you're missing and if you repeated anything. Okay? So we're going to look at, instead of writing all these down, how Pascal's triangle can help us here. Some things to remember about Pascal's triangle if you haven't worked with it for a little while. The top row of Pascal's triangle is 0. So if we identify the rows of the triangle, this is row 0, row 1, row 2, row 3, row 4, etc. Okay? When counting the elements in a row, or the numbers in a row, begin with 0. So the 1, down this entire first line here, when you're counting across, that's always your 0th number in the row. So here's how Pascal's triangle can help us. The first example, where you had 3 snacks to choose from, and you can pick 2 of them, means to look in Pascal's triangle in row 3, element 2. So row 3 is right here. Element number 2, here's element 0, element 1, element number 2, the one we want, 3. 3 combinations. That's what we came up with. The second example here, having 4 options, 4 cats, and bringing 2 to the vet at a time means to look in row 4, element 2. Well, row 4 is right here. Here's element 0. Here's element 1. Here's element 2. That's 6. 6 combinations, which is what we found by writing them all out. All right, let's go to where the work begins. You've raised 6 animals on your farm: an alpaca, a bunny, a cow, a duck, an elephant, and a fish, and can bring 3 of them to present at the county fair. How many different combinations of animals can you bring? Use Pascal's triangle to help you, then write all possible combinations to confirm. So if you've kind of noticed the pattern here, the number of options is your row. We have 6 options. So we're going to be looking at row 6. And the number we can choose here, our choices, is the element. And we can bring 3 of them at a time. So row 6, element 3, will tell us the number of combinations or animals that we can bring. So we started writing the rows down the side here. Let me continue. Here's row 5. Oh, why is it writing in blue? Here's row 5. Here's row 6. That's the one we want. And we're looking for element 3. Here's element 0, element 1, element 2, element 3. There are 20 combinations. I'll get you started. ABC is a combination. Let's keep A and B the same and now include D. Let's keep A and B the same and now include E. Let's keep A and B the same and now include F. Those are all the different combinations that can start with AB. ABC, ABD, ABE, ABF. Now, let's keep A the same and start with C. What are all the different combinations that start with AC? Well, ACB has already been written right here at ABC, so we're going to start with ACD. Keep AC the same, ACE. Keep AC the same, ACF. Okay, let's keep A the same again, and now go to D. What are the combinations that start with AD? Well, ADB has been done. ADC has been done. We can do ADE or ADF. Let's keep A the same, and we'll start with E. Or next put E. AEB, done. AEC, AED, all done. The only combination is AEF, right? And we don't have to write anything that starts with AF because AFB, AFC, AFD, AFE, they've already been written down in a previous combo. So these are all the different combinations that start with A. And we did this logically by going AB, C, D, E, F, AC, D, E, F, AD, E, F, and then AEF. So now we're going to start with all the B's. Okay? I don't need to start with BA because all my A and B combos, whether it's AB or BA, are all included here. So I'm going to start with BC, right? I've already done BCA. I mean, really, an A should not show up again, right? Because every combination that involves an A has already been written down. So I'm going to start with D here and continue that logical pattern through until you get what you know you should get, which is 20. Then the next one. So we're not done here yet. You've got some work to finish here. You're using a coupon for a large 5-topping pizza, and there are 7 toppings: anchovies, bacon, chicken, mushrooms, olives, pineapple, and sausage. And you can choose from. How many combinations of pizzas exist? Use Pascal's Triangle to help you, then write all possible combinations to confirm. So again here, you're looking for the number in Pascal's Triangle that tells you how many combinations there are. Your number of options is your row. Your number of choices is the element. So once you figure out how many combinations you're looking for here, you can start to write them out again in a very logical way, like we did with the previous examples. Again, this is something to where potentially on a map test or high school placement test, if you don't have Pascal's Triangle memorized or handy, which I wouldn't necessarily expect you to do, writing out these combinations logically, okay, can be an option for you to figure out the total number. Then we move on to our probability tree. We went through how to make this tree in the algebra video. Your question here, a box contains 3 yellow chips and 5 blue chips. 2 chips are drawn at random, 1 at a time from the box with replacement. So really the same question as you had for, or same situation as you had for algebra. Using a probability tree, calculate the probability that at least 1 chip is yellow and at least 1 chip is blue. Okay, so it doesn't matter which one you draw first, or if they're both yellow, for at least one's yellow. If they're both blue, for at least 1 chip is blue. So you can actually use the same probability tree as you wrote for algebra, but then you're just answering different questions with that. Then we move on to our, and again, I should say, please write your geometry answers in your geometry packet and your algebra answers in your algebra packet so I know where I can find them. You can do your tree in either, just tell me which one, but the answers to those questions should go in the particular packet. And lastly, we have our Polyaminos. Each of the 12 appears in the figure exactly as it appears on the left, no turning, rotating, flipping, or whatever. You need to identify where they are. Would it be funny if this ball is actually not that one, but like a combination of that and that? That'd be kind of funny. I don't think it is, but that would be funny. Anyway, identify where in each figure each polyomino is. Highly recommend you use pencil for this. Highly recommend you turn in your math packet early for me to check over, especially if it's a square on your bingo board. But that's all we have for this one. Have a great break and a great day. Don't forget to like and subscribe. Talk to you soon. Bye.